Ladies and gentlemen, before we discuss anything at all, it is important to know that before we begin a panel data econometrics, we want to just refresh your mind with cross-sectional model that we've been dealing with all along. So what you see on your screen is a cross-sectional model. Cross-sectional, okay? And what makes it cross-sectional? It's cross-sectional because you can see that we have I. We have I. We have I. And this I is an important thing because that I is indicating that it is cross-sectional. It is changing across individuals. So Y will be different from person A, person B, person C, or city A, city 2, city 3, city 4. And that is how it's taken. It's not changing across time. So there's no T. And the number of I's are from 1 all the way to the total number of I's. Okay, it's from 1 to the total number of I's. Okay. Oh, somebody says I'm not showing the slides. So did you say I'm not showing the slides? All right, let's move on. So you see it. So this is an important information. Cross-sectional, that's what we've been dealing with. So if you can remember the ones we dealt with some time ago, let me just take you back. We dealt with something like Y is equal to alpha plus, let me say beta x1, okay, plus gamma or lambda x2 plus mu x3 plus delta x4, and then plus epsilon, the error term. Okay. Now, so you can see that, and this is I can put an I here. The I here is indicating that this information is a cross-sectional data set. So we don't have time dimensions. Now watch the next one, and you see the difference here. Now in this one here, this is a time series. The same thing, as you can see from the above, the same thing, but this time the time has been added, but no I has been added. So each particular variable has got a T. The T is indicating that it only changes across time. So Y is changing across time. So if it is inflation, is inflation changing across time? So the observation is just 1. So we are talking about, say, just Ghana. And we have only Ghana, and we are calculating Ghana's interest rate, Ghana's inflation, Ghana's exchange rate, and these ones are changing over time for only Ghana. That's a typical example of a time series model. So that's why you see that the T starts from 1 all the way to the total number of time periods. Now let's combine these two into the final one, which is known as cross-section. Okay, let me just clear the information content here. So when you clear, before I come to panel, okay, before I come to panel, or let me just quickly do the panel. So in a panel situation, you can see that observations are changing across individuals and across time. Each dependent variable and independent variable are all changing across individuals and across time. And the error, please note that the error will be represented with its epsilon, with U, or some other things. Okay. The error is also changing across individuals and across time. And you can see that if we talk about autocorrelation, that will be very, very powerful here, because the observation may be correlated with itself across individuals, okay? And then the observation will also be correlated across time, okay? So you are correlating yourself with another observation and correlating yourself with your previous year, your own self's previous year. And that is the interesting thing about correlation. So the autocorrelation, the serial correlation is much more pronounced in a panel. So this is a typical example of a panel data set, a general panel data set, okay? I'll come and talk about a composed. But before we dig deeper into panel, I want you to look at the assumptions of cross-section. Because once you understand the assumptions of cross-sectional model, It will help you to appreciate what we shall be doing in the panel regression. These are the main assumptions. They are not the all, but the main. The first assumption is that the expected value of the error term must be 0, given the other independent variables. So the expected value of this error term, let me just showcase it properly. The expected value of this error term, given the explanatory variables, the independent variables, is 0. Okay, now what does that mean? What this means is that this is the assumption we call the normality assumption. Okay, the mean of the error term should be 0. It is also an assumption that is an important assumption because without this assumption, if the error term, if the correlation between the error term, okay, if the explanatory variables is not given, if this xi is not given, then we have an issue of endogeneity. And I'll come and talk about endogeneity properly. Okay. But in this context, there is exogeneity, but it's a weak exogeneity. When we come to a strong exogeneity, you will again appreciate it better. The next assumption is homoscedasticity. We know this already from cross-section I did, where the variance of the error is constant. We know this. What is the meaning when it's not there? When it's not there, it means that the variance of the error is heteroscedastic. And that means that the coefficients are going to be inefficient. That we say they are not blue, or they are not best linear unbiased estimators. The next assumption, which is a cross-sectional assumption, is that the covariance between the current, this error term and a different error term should be 0. So there must be no serial correlation. What if this assumption is violated? If there is autocorrelation, it means that the beta cap, the estimated values, will be inefficient. Then there is an assumption of no endogeneity. But a simple assumption of the endogeneity says that there must be no correlation between the independent variable and the error term. Remember, the error term is unobserved, and then the independent variable is observed. So there should be no intercorrelation between the observed and the unobserved. That is an assumption of no endogeneity. In other words, their dependency must be 0. And then we had the assumption of no perfect collinearity. The assumption that says that the explanatory variables must not be correlated with each other. In a panel data, this is called strict exogeneity. Because what it means is that the expected value of the error term given the independent variables, okay, and another error term over a different time period, okay, should be 0. In short, the explanatory variables, or what we call the regressors, must not be correlated with each other. Now, when there is, and this is just what we've done before in cross-section, when there is a problem with heteroscedasticity or autocorrelation, we use something known as the GLS, something we did to it. Or you can use a newer West, which we spoke about. But when there is endogeneity, which you will learn in panel, okay, you will use something known as instrumental variable regression. And there are 2 of these instrumental variables. This is the thing we are going to study last. Okay. There are 2 of these instrumental variable regression. We will understand endogeneity properly, don't worry. Okay. And then the first is known as 2-stage least squares, and then the GMM, the generalized method of moments. Those are ways to deal with some of those problems there. So in a panel, you come to learn that in a panel, we go beyond just heteroscedasticity and autocorrelation and look at more other issues or bigger issues. So those things are not big issues because they have been corrected in cross-section, but we have to deal with them properly in a panel. Now, let me take you back to the general panel model. This is a general panel model. Now, pay attention here because this is critical. This is a general panel model, but the error term is an important terminology. This error term is all the panel model is about, more or less. The error term, that's what defines the entire panel model. And this is another way of rewriting the panel model. Okay. This is for those who do the DEA efficiency, where on the left-hand side, the dependent variable is given by efficiency score, a performance score. And then you have other strange elements on the right-hand side, the Z variables and all of that. But I'm more interested in the middle one. Now, in a normal panel, you will come to learn later that the constant, which is the alpha here, is not too important to us, because over time, it will whittle away. But we are interested in the explanatory variables. And all of these explanatory variables are said to be exogenous, which means that nothing is determining them. They are observables and they are not affected by anybody. Okay, they are not influenced by anybody, but they influence the why. The error term is the key and the most important thing. It is made up of 3 elements, and you need to understand every one of them, because it is this that make the panel. Well, as you can see, there's one which has I and no T. So that will indicate to you that this is what is known as individual specific effect, or what is the individual heterogeneity. Okay, that is like individual heterogeneity. Sometimes it's called unobserved heterogeneity. Now let's talk a little bit about that, and then we come to these ones. Okay. Every other thing here is self-explanatory. Let's talk about that one. First of all, the xit is a vector of one or more observed independent variables. So the xit is a lot of them. That's why the reason why we say it's a lot of them is that that's why you have something like, with a beta to the transpose, because it's quite a number of them. So usually there's a lot of explanatory variables. And these explanatory variables sometimes are called environmental variables. They don't include a constant, and they are always indexed by time and individual, both individuals or units as well as time. Okay, then this error term I spoke about. The error term is made up of the following: the UI, the lambda t, and the epsilon it. Now the epsilon it is always identically and independently distributed with a 0 mean and a constant variance, like every other error term that we know before. But you can see that now the UIT is composed, is made up of all of these. What does that mean? Well, there's something first you need to know before we go there. The UI, let's take them one by one. The first thing, because what is important is not what is equal to, but the element of it, the UI. This UI, sometimes we call it, we attach the coefficient to it. Okay. So I want you to see this UI as like one of the x's. Okay. I want you to see, let me just undo this. I want you to see it as one of the x's. Okay. Like one of the x's. How do I remove this? One of the x's, like that. Okay. So that is one of the x's that you have there. Okay. That you can actually see. Guys, just a second. Okay. So when you look at this xi, okay, this xi will definitely have a beta in front of it, say beta 1. So x1. And then you have something like plus beta 2. So this would be independent variables, as you know. Now I want you to see this UI as one of them. Okay. So UI, I want you to see UI as something like this, but with a beta 3. Okay. So it is like one of the independent variables. But there's a slight difference between it and the independent variable. The fact is that it doesn't change over time. Remember, these independent variables are changing over time. So these ones are xit, are changing across individuals and across time. But this one, this individual, this unobserved heterogeneity is not changing with time. by changing with individuals. And secondly, it's not observed like these ones. It's not observed like them. So we call it a big name called unobserved exogenous time constant. Now, why time constant? Because I told you that it doesn't change with time. Or time invariant, which means that it doesn't vary with time. And it is an individual specific factor. The big name for it, and I wanted to keep this big name because it will keep coming. The big name for it is unobserved heterogeneity. Unobserved heterogeneity. Why unobserved? Because it's unobserved. Okay, an unobserved nuisance is there, but you don't see it. And because you don't see it, it is also in the composer or affecting, like these other variables, the XIT are affecting. It is also affecting the entire regression process. So how do you deal with that? We'll come to it. The key point is that it has no time index. I've explained that already, and hence is assumed to be constant over time. It captures characteristics of the I, that particular person. So if you're talking about any observations, whether it's cities, whether it's persons, companies, countries, those specific characteristics of that city, of that person, of that company, of that country, that are not picked up by the exogenous factors, the other explanatory variables that are changing across individuals and across time. It includes unobserved ability, because you can't observe ability per se. You can't calculate it easily. Unobserved culture. There is an intrinsic behavioral characteristic, quality, a religious characteristics, gender. You see, a person might be behaving where you wouldn't even know the religion of the person, which is dictating why that person is wearing that dress he's wearing. A person's gender might define the way he is behaving. A person's race might define certain actions. And these things, they are specific to individuals. They don't easily change across time. For example, gender doesn't easily change across time. Okay? At least within a year, it doesn't easily change. Race doesn't easily change across time. Okay? Religion doesn't easily change across time. So that is one key aspect of the error time. It can be a dummy variable. Okay, a dummy variable. For example, dummy variable is gender. It doesn't change across time. Okay, it's just 0 or 1. Okay. But some of them might be not 0 or 1, and yet they are like that. But most of these things are usually 0 or 1. They are dummy variables. Okay. And they change rather across individuals. So that is the first element of the error time. Can you imagine the first element of the error time? Now, what is the second element of the error time? The second element of the error time is here. It is lambda t. So as it stands, that one changes across time, but not across individuals. That one is easy. It's symmetric time trend. Sometimes we call it time effect, or a set of varying dummies. So you see, these ones, they vary across time, they change. Controlling for technological changes. For example, regulation, the regulations in the economy, the tax regulation, the budget regulation, these things change across time, but they don't change from household to household. They don't change from country to, They don't change from individual persons to individual persons. Macroeconomic effect, like GDP, is changing across time, but it's not changing across individuals. Inflation is changing across time, but not changing across individuals. Okay, so that lambda t, it is something that is changing across time, and you can use it to help you to know the behavior of the dependent variable over time. You will know, based on this, you will know how the dependent variable is changing over time. It is said to be a contemporaneously exogenous to the conditional error. It's not part of the error time. And there can be more of it. So that lambda t, you can have plenty of it. It can be a dummy variable for each time. So let's say you have 2001 to 2010. Then it means that that dummy, that time period is going to be, for 2000, that is for this, 2000, 2001, okay, 2002, 2003, and finally 2010. And each one of them will have a kind of a coefficient, which is telling you how the variable was changing when we got to that time period, 2004, 2005. So you can have, kind of an equation representing all of them combined. That is a symmetric time trend. And finally, the usual one, our usual error term is there. Okay. This will capture all other unobserved factors, the noise. Okay, the noise. Now, ladies and gentlemen, depending on the way you model the behavior of these things, you can have different panel data models. And next time, what we are going to do is I'm going to give you a specific panel data model, and then we'll see how we do the modeling of this panel data model and the different ways of looking at these panel data models. But for now, what we've just done is this. We've looked at this simple panel, well, it's not simple, this panel data model, and we've looked at the element. Remember, this is exogenous, the XT is exogenous, and it's changing across individuals and across time, okay? This one is changing across individuals and across time. Okay. Then we spoke about the composed error term, this one, the composed error term, which has several things, 3 things. We call the first one the unobserved heterogeneity, the individual specific effect. Then the time heterogeneity. This is unobserved individual heterogeneity. This is unobserved time heterogeneity, or the time dummies, or the time specific effect, which is changing across time, but not across individuals. And then finally, the noise. The noise changes across time and individuals. That is the end of the first part of our panel data for today.